Hello, everybody. Thank you for joining me today. My name is Carol Francis. I am a senior GIS analyst at GISTIC Research in Tempe, Arizona. At GISTIC, I work on projects related to analyzing and visualizing transportation data. I have created numerous Tableau, Esri, and Google Data Studio dashboards and developed FME processes that generate highway log products and a process that creates polygonal boundaries from non-spatial event data. I have a Master of Science degree in GIS from the University of Arizona. I am an FME certified professional and I am active in the Arizona chapter of Women in GIS, the Arizona Geographic Information Council, as well as the FME in Transportation Special Interest Group on LinkedIn. I am here today to talk to you about a couple of FME processes I developed that generate summary and detailed log products for the Arizona DOT. For those of you who are unfamiliar with highway logs, a detail log is a complete inventory of DOT-owned assets within a state. A summary log is a summary of centerline, lane mile, and maintenance lane miles on state-owned highways. ADOT published these logs annually until they implemented roads and highways in 2015. The implementation of roads and highways was such an enormous upheaval of their old data management systems that their old highway log workflows were now obsolete. About 1.5 years ago, ADOT asked GISTIC Research to resurrect their old highway log program. I'm going to give you a brief overview of the FME processes that overcame the 6-year hiatus of the state highway log program. As I tell you more about this project, we'll visit challenges we encountered, the general process workflow, the process output, and the benefits of the process. Traditionally, highway logs are printed reports. Historical ADOT summary log reports are a few dozen pages long, listing summary statistics about routes within the state, divvied up by boundaries such as counties or federal land ownership. The historical detail log reports are enormous documents of approximately 800 pages that display assets such as bridges, intersections, and slow vehicle pullouts listed in milepost order along a route. The main goal of this project was to improve upon and modernize the traditional highway logs by providing users with self-service multi-format SHS log products. In other words, we supplement the traditional print output with dashboards that allow users to dial into smaller areas of interest. The simple and user-friendly dashboards complement the Esri Roads and Highways system, of course, with some FME manipulation between the Roads and Highways database and the dashboard interfaces. As I mentioned previously, there was a 6-year break between the implementation of Esri Roads and Highways and the publication of the highway logs. Implementing Roads and Highways completely destroyed previous highway log workflows, and the reporting platform built into Roads and Highways, called Roadway Reporter, isn't quite able to create the reports that ADOT needed due to the complexity of their data. The data used to generate the highway logs actually resides in 3 different data silos, the vast majority of which is in Roads and Highways. However, there is bridge data in the NBI database and maintenance boundary information in a data silo that ADOT affectionately calls PACOS. Each of these data silos uses a different location referencing system. Roads and Highways uses a route and measure referent, NBI uses XY coordinates, and the PACOS system uses a route and milepost referent. There is also an incredible amount of information contained in these logs. The detail log displays the output of an overlay of 28 data sources, such as bridges, pavement, shoulder type, shoulder width, intersections, and mileposts. Relatively speaking, the summary log process is pretty straightforward. It performs a series of overlays on 17 feature classes, the output of which allows us to add up center line miles, lane miles, auxiliary lane miles, including shoulders and bike lanes, and maintenance lane miles, divvied up by route, engineering district, county boundary, and federal land ownership. This process outputs 480 nice and tidy non-spatial records into a SQL table. This SQL table is used to populate a Tableau dashboard and a SQL Server reporting services. Both offer self-serve platforms for users who may dial into the dimensions they need information about. The SSRS platform also allows for the generation of PDF reports for people who want a traditional paper version of the report. This is what the end users see. This is a screenshot of the Centerline Tableau dashboard. The users may use the Group By radio buttons to choose the dimension displayed, and they may toggle between a tabular and bar chart view of the results. The lane miles dashboard follows the same graphic themes, but displays lane miles and maintenance lane miles. And this is what the SSRS report looks like on the server. The PDF output from SSRS is published on the ADOT website. Now I'd like to talk to you about my baby, the detail log process. This thing is a beast. It reads 28 data sources. 25 of those are shapefiles or feature classes, and 3 of them are flat lookup tables. It uses 318 transformers to generate about 40,000 records that are written both to ArcGIS Online and a table on our SQL Server. The output is then consumed by SQL Server reporting services and displayed in an Esri dashboard, which is nested inside an Experience Builder. This flowchart illustrates the process flow. First, we do an overlay of all linear full coverage events with ADOT-owned routes to define the scope of the process. Then we convert the linear events that have partial coverage and polygonal boundaries to points with length attributes, mix these in with the true point feature classes, and do an event point online overlay with the output of the previous overlay process. Then we tidy that output and write to an ArcGIS Online feature service and our SQL database. The data read into this process falls into 6 categories: linear full coverage feature classes, linear partial coverage feature classes, point layers, the route network, including carriageway descriptors and ownership, boundaries, including polygonal and event layers, and lookup tables to enhance domains. For each input group, the data is read and the columns are standardized in preparation for the next processing steps. If a feature class has full coverage, meaning it covers the entire route network, we combine all linear records into one stream. First, we standardize the columns in the data stream, then send the entire stream to an overlay process where the stream overlays with itself. We call this a single stream overlay, which we accomplish using a custom transformer that Bo Guo from Gistic developed. This transformer is available on the Hub. The resultant output is a series of events where each event describes the shoulder surface, pavement type, number of through lanes, shoulder width, surface width, and the length of an event. The screenshot is only a tiny sampling of the output of this massive overlay of 6 feature classes. I mentioned on a previous slide, we pull a bit of an interesting stunt in this process. Every data source that is not a full coverage event feature class is treated as a point. We convert lines and polygons to points and throw them into the Event Point Online overlay process with the true point feature classes. This works because we capture the length of each event, so the output of each linear or polygonal point contains a route measure and a length attribute. This table illustrates what the linear, non-full coverage events look like after being converted to points. The symbol column is populated with a lookup table that gives an abbreviation for every source feature class name. Here we have slow vehicle pullout, left turn lane, right turn lane, left turn lane, etc. The data column describes the event with more textual information. Finally, all point streams are combined and the point stream goes to an Event Point Online overlayer. where the point stream is overlaid with the linear full coverage event output of the single stream overlay process. The output of this part of the process is event point format with a measure and a length value. We use a quick SQL script to obtain milepost and offset attribution and a bit of attribute cleanup, such as deleting duplicate spaces caused by field concatenation. Now we have a detail log where every important asset on ADOT routes is marked with a point. This screenshot illustrates the final attribute schema. The various points, not full coverage feature classes, and polygons are captured with the symbol and data columns. Every segment of roadway contains these attributes that were derived from the full coverage feature classes. The features that have null length values were derived from feature classes that have true point geometry. Using FME also allowed us to discover, report, and track the editing of numerous data bugs. We unearthed data bugs that had not been detected previously because nobody had tried to create relationships between the previously disconnected data silos before we started this project. As you can imagine, defining, reporting, and editing these data bugs was a project in itself. We check for alignment with business rules. For example, if a structure goes over a roadway, does the overpass have clearance high enough to allow for a vehicle to pass under? We also run checks to ensure that the data contained within the disconnected silos agrees amongst the silos. For example, does the structure length in the NBI database match the structure length in the GIS database? We also ensure that there are no missing or null attributes where values should exist, such as ensuring every mile of roadway has a shoulder width value. Once we were confident with our process and our data quality, we validated the output using a combination of 6-year-old highway logs, individual feature classes in the Roads and Highways database, photo logs, and Google Street View. This combination allowed us to ensure that our output matched the source data and what is visible on the road. The FME process writes to an ArcGIS online feature service, which powers a user-friendly dashboard that is deceptively simple. I'd like to point out a few things. The full coverage feature classes populate these columns. Partial coverage feature classes, points, and polygons are used to populate the symbol and data columns. And since one of the goals of this project was to promote continuous improvement, this dashboard also allows users to report any errors they find using the known issue locations and report an issue buttons. If a user finds an issue, first they click the known issue locations button. If their issue is not already listed, the user may then click the report an issue button. Information written to this form populates a feature class that is monitored by data editors who will rectify the issue before the next run of the FME process. Using FME, we were able to resurrect the Arizona Department of Transportation Highway Log Program by providing users with self-service, multi-format SHS log products, which facilitate continuous improvement through data validation and user input. Thank you again for joining me today. Please feel free to reach out at any time if you have any questions or would like to discuss these processes further. Thank you.